Lesson: Layered Design in AI Models. Layered design in AI models serves as a cornerstone strategy in the development of sophisticated artificial intelligence systems, offering a structured approach to managing complexity and enhancing model performance. This concept is pivotal to the architecture design principles of AI, enabling professionals to construct models that are not only efficient, but also scalable and adaptable to various tasks. The layered design approach involves organizing the model architecture into distinct layers, each responsible for specific computational tasks, thereby simplifying both the design and implementation processes. A key advantage of the layered design is the modularity it introduces into AI model development. Each layer in a model performs specific functions, which allows for easy troubleshooting and modification without affecting the entire system. For instance, in neural networks, this modularity is evident in architectures like convolutional neural networks and recurrent neural networks, where convolutional layers handle spatial hierarchies of data and recurrent layers manage sequences, respectively. These layers can be adjusted, replaced, or enhanced individually to optimize performance, demonstrating the flexibility offered by layered designs. Practical application of layered design in AI models can be significantly enhanced through frameworks such as TensorFlow and PyTorch. These tools provide robust environments for building and fine-tuning various layers of a model. TensorFlow, for example, facilitates the construction of custom layers and the integration of pre-built ones with its Keras API, which streamlines the model building process with high-level abstractions. PyTorch, on the other hand, offers dynamic computational graphs that allow for real-time changes to the architecture during training, providing a more intuitive approach to handling layers. To address real-world challenges using layered design, consider the problem of image classification. A CNN can be designed with multiple convolutional and pooling layers to extract hierarchical features from images. These layers progressively learn to identify simple patterns like edges and textures, and then more complex structures such as shapes and objects. By stacking layers, a CNN can effectively capture spatial hierarchies, making it a powerful tool for tasks like facial recognition or autonomous vehicle navigation. In reinforcement learning, layered models are employed to separate policy learning from value estimation. The actor-critic model, for instance, uses a layered approach where one network determines the best action to take, while another evaluates the action by estimating the return. This separation of concerns allows each component to specialize and improve independently, leading to more efficient learning. The success of layered design is also evident in natural language processing tasks. Transformer models, such as BERT and GPT, utilize an architecture where attention mechanisms are layered to capture contextual relationships between words in a sentence. Each layer in a transformer model refines the representation of the input data, enhancing the model's ability to understand and generate human language with remarkable accuracy. Layered design is further exemplified in the realm of transfer learning, where pre-trained models can be fine-tuned for specific tasks. By freezing certain layers and retraining others on new data, models can leverage existing knowledge to quickly adapt to new problems. This approach not only reduces the time and computational resources required, but also improves the performance on tasks with limited data. To implement layered design effectively, professionals should adopt a systematic approach to model development. Initially, defining the problem and understanding the data is crucial. This involves selecting an appropriate model architecture that suits the task. For example, selecting a CNN for image-related tasks or a transformer for NLP applications. Next, leverage frameworks like TensorFlow or PyTorch to build and customize the layers of the model. These tools offer pre-built functions for common operations, allowing developers to focus on fine-tuning and optimizing the architecture. Once the model is constructed, training involves feeding data through the layers, adjusting parameters to minimize error. Here, visualization tools such as TensorBoard can be invaluable, offering insights into the model's performance and highlighting areas for improvement. This iterative process of training, evaluation, and modification is central to refining the layered design until optimal performance is achieved. A case study illustrating the power of layered design is the development of AlphaGo, the AI program that defeated world champion Go players. AlphaGo utilized a deep neural network with multiple layers to evaluate board positions and determine optimal moves. The layered design allowed AlphaGo to process vast amounts of data and learn complex strategies, demonstrating the effectiveness of this approach in solving intricate problems. Statistics also underscore the impact of layered design. A study by He et al. On ResNet, a deep residual network, showed that increasing the number of layers improved the model's accuracy on image classification tasks. ResNet's architecture, which involves stacking residual blocks, exemplifies how layered design can lead to breakthroughs in AI performance. In conclusion, layered design is a fundamental aspect of AI model development that enhances modularity, flexibility, and performance. By organizing models into distinct layers, professionals can tackle complex problems with greater ease and efficiency. Tools like TensorFlow and PyTorch facilitate the implementation of layered designs, providing the necessary infrastructure for building and optimizing models. Moreover, the versatility of layered design is evident across various domains, from image classification and reinforcement learning to NLP and transfer learning. As AI continues to evolve, mastering layered design will be crucial for professionals aiming to implement effective and scalable AI solutions.